All right, so welcome back. Now we're going to fix up that issue of multivaluedness and all that jazz. So how do we do that? All right, well, let's now think sort of what seems to be tangentially for the moment about what I'll call conservation laws. So let's call rho of x and t, that's like the density of stuff. That's the amount of stuff per unit length. And stuff, I'll not say what it is, it's something. Okay, if I take an interval a to b and I integrate this, I get the amount of stuff over this interval. Now the goal is to figure out something about how this changes, so let's put d by dt of this. Right, that's the rate of change of the amount of stuff over a to b. So what could that be? What could that equal? So that's the rate of change of stuff. Well, if this thing's being moved around, if it's being transported, then there's the transport in and out of my interval, and there's also a possibility that there could be production or destruction. You know, when I think about temperatures, right, I can think about the amount of heat over a section of a rod. There's transport of heat in and out because things diffuse. You know, the temperature diffuses around, but I could also have a heating element or something cooling the thing. All right, so that's what I have here. Let's just sort of formulate this a bit more mathematically. So I've got d by dt of the integral from a to b of rho dx is equal to, well, the transport in and out, I'll represent that in terms of fluxes. So if I take J to be the flux, so that's the flux of stuff. All right, then the flux in is going to be, if I'm thinking about things going in the positive x direction, the flux in will be at A, right? That's the flux coming into the interval from the left, and then there'll be a flux going out at B. So J of x and t minus J of B of t, that's going to be the transport in and out. And for production or destruction, I'll just write that as an integral over some density S of x and t dx. I'm putting S up there for a reason. Okay, so this is the integral of the source or sink density. All right, so that's an equation. It tells me, you know, what happens to the amount of stuff. It tells me how much of the stuff is conserved. So there's an equation expressing how much is conserved. It's a conservation law. And I'm just going to write this as an integral conservation law. And the reason why I'm calling it an integral one is that there are integrals that appear in here. And of course, that's a little bit of a contrast for what we're talking about in this course, which is partial differential equations, like that one. This is not what this is. This is something that's got integrals in it. It's an integral conservation law. However, having said that, there is a differential version of this. So there's a differential conservation law that I'll derive in a minute. And that's the connection from here to here. Okay. So we've got stuff. It's moving around and it could be produced or destroyed. We have a conservation law, an integral conservation law that's describing that mathematically. Right, so let's now derive the differential version. So the way that we do that is we come along and we write this whole thing as a single integral. Now at this point I should also emphasize that we've just chosen some particular interval a to b, And we didn't actually say what A and B were. They sort of could be anything. So they're arbitrary points. And that's going to be part of the argument that we make now. So A and B are arbitrary points. We've got this interval, the ends of which could be anywhere. Okay. So let's just write this as one integral. So the first thing I'm going to do, these are constants, so I can take the d by dt and I can slap it on the row. But when I take the d by dt there and slap it on the row, I'm holding x fixed in the two arguments of rho, so that becomes a partial derivative when I slip it inside the integral. So that's the first term. Now this one, let's take everything over to one side. So that is, I'll just write that as plus j of x and t between a and b, and then I've still got that one. I've got my dx there. So that equals to 0. So that's manipulating that. So far, so good. Okay. Now, the only term that doesn't have an integral on it is this one. But that's just the integral from a to b of dj dx. So I can recognize that all three terms here are integrals over the same range, and I can now just slap them all together and write a single integral. What do I get? Rho t plus jx minus s. That's the integrand, dx is 0. Now here's the argument. Since a and b were totally arbitrary, they has to be true for any old endpoints. And the only way I'm going to get that to be true is if the integrand itself is 0. Another way of saying it would be to say, okay, well, let's take a and b to be arbitrarily close to one another. That means that I evaluate the integrand at the point times the distance between a and b. It's got to be 0. The integrand is 0 again. So rho t plus jx is equal to s. That's the differential form of the conservation law. All right. So we've got two versions. We had the original integral form. We've now got the differential form. All right. Let's give an example of this sort of thing. It's a nice example that's very popular in this business. E.g. traffic flow. Right, so here's the picture. We've got a road, we've got a bunch of cars on it. Rho here is the car density. And we're going to make some approximations to simplify the whole thing so that it's transparent and straightforward. So we're only going to consider cars going one direction. We're not going to be thinking about cars coming the other direction. And then we're going to say that there's no overtaking. Overtaking is going to complicate things. So we're not going to allow for that. We'll just say that each car can only, get up close to its neighbor. It can't get past them. Okay? And then we'll also say that there's no production or destruction of cars. That means there's nothing like side roads or parking. So cars cannot disappear from the lane of traffic. So with all of those extra assumptions, what we're going to say is that we have a car density, right? And cars have to be conserved. So we're going to have a conservation law like this, in which we're going to throw away the source term. So we've got rho t plus jx is equal to 0. Rho is the car density. All right. Obviously, when we're either here or there, and now here, in order to fully come up with a model of something, you need to say what the stuff is. Well, we've said that there's cars down here, but we also need to come and we need to specify the sources and sinks and the flux. So that depends upon the physical or biological or whatever context you're dealing with. The model requires you to specify the flux and the source and sink density. Here we've eliminated that by taking some assumptions, but we still need to say what J is. So what is J? Well, if I have cars, for example, they're moving at some sort of a speed, let's call that V. So the car speed is V, and then the flux of cars, well, that would be equal to the density times the velocity. All right, so that would be J. J is rho times some car velocity, and we need to say somehow what the car velocity is. So one option would be just fix it, but that's obviously not what's going to lead to an interesting problem. All right. Well, we're interested in the fact that we're interested in a traffic flow problem. So when traffic is dense, things ought to slow down. When traffic is light, things are going faster. So in other words, the car speed should somehow depend upon V. Sorry, V should depend upon rho. All right, so it's density dependent, and as a simple model, we're going to say that it decreases with the car density. Right? If there's no cars on the road, you go really fast. If there's lots of cars, you slow down, and at some point you jam up. So let's put that information in by saying that V is 1 minus rho. So I'm going to scale things. I'm going to scale the density so that when rho gets to 1, that corresponds to a traffic jam. You're packed on the highway or whatever, you can't move. So rho is 1 corresponds to jamming, coming stationary. And then, when rho is equal to 0, that's when there's no other cars on the road. I'm traveling at speed 1 here. That's the fastest I can go. So that's a model for traffic flow. So J is going to be rho times 1 minus rho. Okay, so having said all of that, now let's get back to solving this as a PDE, because at this stage we're very close to that. Let's see it. Right, so our model problem. Let's make it completely explicit so that we see what the differential form of the conservation law really looks like. So J is rho 1 minus rho t plus rho 1 minus rho d by dx is 0. That's J, right? So this is rho t plus 1 minus 2 rho x is 0. So there it is. We've got that U is equivalent to rho. We've got C is equivalent to 1 minus 2 rho, and there's no S. Right, so the reason why I chose S there is because for the conservation law stuff, it corresponds to the source or sink density. Okay, so traffic flow. That's where we are. Now we're going to do some traffic-like problems. So one of the most irritating things when you're on the highway and you're driving along is you're enjoying yourself, you've got the open road, but then you hit a bunch of cars ahead of you, and if you can't overtake, you have to slow down. So let's talk about the pile-up problem. All right, so we're going to solve this subject to a specific initial condition. So rho of x and 0 is equal to something. What's that something? Well, let's draw it down here. Okay, so what I'm going to do is I'm going to say that I have no cars at the back, and I've got a line of cars at the front. That's density rho 0, and then there's some sort of a ramp between the two, and it ramps up from minus epsilon to plus epsilon. So that's the initial condition. So it's going to be 0 if x is less than minus epsilon. It's going to be rho 0 if x is bigger than epsilon. And then a linear ramp that goes between these 2 points is 1/2 rho 0 1 plus x over epsilon. That's over that range. Okay, let's just double check that it works, right? So when x is equal to minus epsilon, then this becomes 0, matches up to that. And when x is equal to epsilon, that becomes 2, so it matches up to that. It's a straight line. Okay, so that's our initial condition. There's the PDE. We can adapt all of this. So the characteristic equations, what are they? Well, they tell us that dx by dt is equal to this coefficient, and d rho by dt is equal to what's on the right hand side, 0. So rho is constant along the characteristics again. That's a great simplification. That means that here we can just treat rho as a constant and integrate it. So that means that the characteristics are straight lines. And we've got that x is equal to x0 plus 1 minus 2 rho t. And then if we, let's call this thing f of x in accordance with our usual notation. So this is going to tell us that rho is f of x naught, which is f of that thing, x minus t plus 2 rho t. And we're back to having an implicit solution. Okay. The good thing about this initial condition is that if I feed this in there, then I'm going to be able to solve it. Right? I solved it previously when I had that parabolic hump. I had to solve a quadratic in this case. In that case, here it's actually linear. So I'm going to solve a linear equation, which is even easier. All right, so let's do that. Okay, so we'll get rid of this. I have this. Let's get rid of my sketch and everything. So what I'll do is I'll put up here some essential details that I'll keep for later. So what should we keep? Well, it'd be good to keep some of this stuff. So we've got x is x0 plus t minus 2 rho t. And then we've got that rho is equal to f of x minus t plus 2 rho t. Those are the characteristics equations, right? And we've got this particular initial condition here. We want to solve this. So we'll do that presently, but I don't need this lot. And at this stage, I've kind of got everything here. Let's just give ourselves more room. Great. So there's one slight awkward thing, which is that when we solve this, we've got this 3-branch structure again. So in principle, when you solve the thing, you need to solve it for each piece. The bit that I was talking about, solving the linear equations, is just the middle piece. Let's write things out. So rho of x and t, well, that's going to be 0, right? Nothing changes in rho, right? If f is 0, rho stays 0. So that's going to be for x0 less than minus epsilon. Rho of x and t will be rho 0, nothing changes. If x0 is bigger than epsilon. And this part here tells us that rho is equal to 1/2 rho 0, 1 plus, now that's x0 I get from here, so that's x minus t plus 2 rho t divided by epsilon. That's between minus epsilon and x0 and epsilon. Right, so that's the initial condition now translated to the full solution in view of that. So the only bit of algebra I need to do is in this case. I get from here rho is equal to 1/2 rho 0. This is just solving it. I get that. That's for this case. All right, now it's all explicit. That's good. Now, that's fine. The issue obviously is going to be, I need to be a bit more careful about what these limits are. So let's just do that. So we have x0 is equal to x minus t plus 2 rho t. And if I put minus epsilon in there, well, when I have x is equal to, x0 is equal to minus epsilon, that's where rho is 0. So that's 0. So actually, x0 is equal to minus epsilon corresponds to x is equal to t minus epsilon. So that's when x is less than t minus epsilon. Similarly, I can do the same argument in this case. So now if I switch the sign there. All right, so what happens if I put x0 as epsilon? I get x minus t. Now rho, on the other hand, when I reach epsilon, rho is rho naught. So actually that's what I have now. So x, in this case, is bigger than epsilon plus t minus 2 rho naught t. And this condition, let's just write that out again. That's or. That. And you'll see that they coincide if I put t is equal to 0, right? Okay, so I've got this. I may as well replace that with that. There it is in all of its glory. Okay, so we solved the problem completely. At this point, nothing looks untoward. However, your spidey senses are probably tingling because we know, having looked at the previous problem, that when you have these sorts of implicit solutions for these quasi-linear equations, PDEs, then there can be a disaster because the solution goes multivalued. And if I look down there, something untoward is going to happen when t is equal to epsilon divided by rho 0. This thing diverges, right? So something's going to go wrong, clearly. Let's bring that out by drawing the characteristics diagram. Right, so we're going to have t, we're going to have x. We've got this three-piece section to the initial condition. All right, over here we've got rho is equal to 0. If rho is equal to 0, we've got x is x naught plus t. So we've got a whole bunch of characteristics that are doing that. Now, on the other hand, when we're out there, that's when rho is rho naught. So we've got x is x naught plus t times 1 minus 2 rho naught. And depending upon the value of rho naught, I'm going to get some sort of a slope. So out here, we've got x is x naught plus 1 minus 2 rho naught t. So it depends if rho naught is bigger or less than a half, right? Let's draw it assuming that rho naught is bigger than a half, so that's negative. So that means that they're all tilting this way. Obviously, there's going to be a bit of a disaster. In between here and here, we've got these values that come from the ramp. So the slope gradually switches over from there to there. So we're going to have characteristics that clearly do something like this. They tilt over from that to that. So the characteristics must cross. So we get the issue again. We get the problem, and if I think about what's actually happening for the solution itself, I can draw that too. Let's do that. Down here, so this is x. This is now going to be u. I've got minus epsilon and plus epsilon. I'm going to exploit the full power of my coloured chalk. So that's rho 0. All right, so what's happening is that these points, they're all moving that way. These points are all moving that way. So you can see what's going to happen. The ramp's going to have to steepen up. It's going to have to tilt up. So if I plot a later time, I'm going to get something that looks like this maybe. And then I can keep on going. I can plot a later one. Looks something like that. And then at some point, I go too far. Oh, you've gone too far. And if I go too far, clearly I'm going to have gone beyond where I should have gone, and I get an overhang. Right, so this is the sequence that I get, right, when t increases. Right, and I've got this region to begin with where things are okay, things are steepening up, we're getting shock steepening, but then things start to cross and I get a multivalued solution. So we get a triple valued solution again. When does that happen? Well, that happens when the solution goes vertical. Let's have a quick look. We're using rho now. I'm going to try not to confuse u and rho. Rho is what I like to use for traffic flow problems. So rho x, what is that? Well, I can just come down here. It's 1/2 rho 0 divided by epsilon minus rho naught t. This diverges at epsilon is equal to rho naught t. Right, t is epsilon over rho naught. So that's actually when the thing becomes vertical, and that corresponds to when the shocks first cross, something like that. So, good, bad, this is t is epsilon over rho naught. So we've kind of fully understood the problem here. Right, so I've gone to the trouble of building this thing up as a sort of a physical model related to traffic flow, writing as a conservation law. We've got the issue again that we found last time. Let's deal with it, okay? So, if I look at this kind of stuff, you really see clearly what's going on. The thing's steepening up, goes vertical. When it's vertical, right, my entire initial ramp is now a vertical face. So the solution just looks like a step. So it's become discontinuous. So a discontinuity has appeared. So let's now think about discontinuous solutions to the conservation law. Let's keep this. That'll be useful later. Let's keep that. This is going to go. Right. Now the issue, of course, with allowing discontinuities in the solution is that when I write down a PDE like that, it's got derivatives in it. It's got x derivatives in it. And if x has got a step, then the derivative's sort of undefined. The derivative of a step is a delta function after all. So that's not a regular function. So that sounds as though, you know, we're in that disastrous situation and nothing can be done. However, the whole point about talking about conservation laws was that there's two versions of the conservation law. There's the differential version, which that's the problematic case, right? It's a problematic example, PDE, because we have space derivatives in there. And putting a discontinuity in makes you break out into a cold sweat. Right? So discontinuous solutions. They're problematic in the differential form of the conservation law, i.e. the PDE. And that's because of the d by dx's. But what about the integral form? Well, what's the integral form? It was d by dt of the integral of rho from a to b dx. That equaled minus the flux between a and b plus the source term. For the physical model, we don't have that, but we may as well keep it along for the ride. So that's our integral form. Now, there are no derivatives, no space derivatives, and I can easily shove in things here that have a discontinuity in rho. So the integral form of the conservation law accepts discontinuities. Let's just deal with them much more explicitly, right? So let's say that between A and B is a position x star where rho is discontinuous. And actually, at this stage, there's no obvious reason why this thing is going to stay in one place. It might shift around, so let's let it be a function of position, of time. Okay, so there it is. There's the discontinuity. It might move. So let's just rewrite this a little bit. So let's split the integral up into two pieces, and within each piece, everything remains continuous. The integrand is continuous. Right, so I'm isolating the jump. Right, so that's what I get there. This thing doesn't care. That's still the flux difference between A and B. And then here I can do the same thing. I can go from there to there. S dx plus x star to b of s dx. Right, that's breaking things up, and you know, with some minimal assumptions on the source and sink density, there's nothing unpleasant in there. Then I'm making sure that by splitting things up at x star, I've got integrands here that are perfectly continuous. Right. Now at this point I'm going to use Leibniz's rule. And I hope you remember Leibniz's rule. But if you don't, here is what it is. So Leibniz's rule is when you are differentiating an integral. So in particular, what do I mean? Well, Leibniz's rule tells me how to differentiate an integral sort of like that. So here we go. So if I have d by dt of the integral of f of x, let's not call it that. I've got an f over here. Let's call it g of x dx. And let's say I'm integrating from a position a, but I'm integrating up to something that depends upon t. Right? Well, Leibniz's rule, if that was all I had, would tell me, well, there's the t dependence. So it's like using the chain rule. I have a dx by dt, and then I get rid of the integral since I've differentiated the limit, and I just put x is equal to the limit there. Right? This is assuming that a is a constant. Right? Now Leibniz's rule is a bit more general than that because it allows me also to deal with cases where I have a t in this function g. Now there's a t dependence there, there's a t dependence there, and when I use Leibniz's rule, it's like thinking about it as a product. So when you think about a product, when you differentiate, you differentiate one piece of it, leaving the other one. That's this. And then you leave that one and differentiate the other one. So actually there's two bits that come in. So there's one is this one from differentiating the limit, and then the other one is leaving the limit and differentiating the integrand. So that's the partial derivative of g with respect to t. So that's Leibniz's rule. Okay, so we can now reconsider our integral conservation law at this point, bearing that in mind. Okay. So I will just now do these two derivatives with Leibniz's rule. So I get the integral from a to x star. Remember this depends upon t in principle. Okay, and I can do the derivative of rho, so I get this term. But then I also get this one, so that's now going to be x star dot and rho, and this is going to be evaluated at x star. But I have to bear in mind that x star is the position of the discontinuity of rho. So actually, what I really want here is that rho evaluated as x goes to x star from below. And I'll just notationally put x star minus to indicate that. So that's the limit from below or from the left, thinking about it in space. All right, so that's what this is. Now if I look at that one, I get plus the integral from x star to b, that's this term, rho t dx. And now I can also differentiate the lower limit, so there's now a minus sign, x star dot, and then I get rho evaluated as x goes to x star. But now it's from the other side, so it's from the right, so I'll put an x star plus, that's the limit from the right. So that's using Leibniz for this term. Okay. Super. Where does that lead us? So it leads us to the following. Ooh, I almost rubbed out my dot there, that would have been bad. All right, so what do I get? Well, I get x star dot. Now, let's use some more notation. So it's rho at x star with a minus sign. Let's just call that rho minus. And this is rho at x star with a plus. Let's call that rho plus. Right, so this is going to be rho minus rho plus. Now there's these two integrals left over. A to x star of rho t. There's another one of those there, right? And then there's a x star to b integral of rho t minus s dx from the combo of this one and that one. And these equal that thing. Right, so this is j at a minus j at b. That's our integral conservation law, where we've explicitly taken account of the discontinuity. Right, that's the limit from the left, that's the limit from the right. Okay. We're in good shape at this point. So, thinking more broadly, how can I learn something from this? Because at the moment, I've simply just restated the conservation law for any old A and B. It doesn't, in principle, tell me anything new. However, I do have the freedom of choosing A and B. And if I look at this equation, how can I use that to my advantage? Well, one thing I can do is I can eliminate the integrals. These things are continuous since I've eliminated the discontinuity. And so if I now let A just get very, very close to x star and B get very, very close to x star, those things converge to 0. Oops, now let A go to x star, and really it's from the left, and B go to x star, really from the right. Integrals disappear. What do I get? Well, I get dx star dt times that equals that. I'm just going to write that as j of x star plus minus j of x star minus divided by rho plus minus rho minus. The shorthand, the extension of the shorthand will be to put this, right? All right, so I learned something from this, which is that if there is a discontinuity and if the flux from one side is not equal to the flux from the other side, right, that's the flux into this discontinuity, that's the flux out of the discontinuity. If they are not in balance, it's got to move. And at this point, discontinuity is a long word, so I'm just going to call it a shock. Right, we called something shock steepening before. We were heading towards a discontinuity. We were heading to a shock. A jump here, this discontinuity, it's a shock. People like to refer to it as a shock. Rarefactions, shock steepening shocks, all of that terminology came from gas dynamics, because that's originally where people sort of worried about a lot of this kind of stuff. So you get shocks in gases and stuff like that. And we're doing it. Our physical model problem is actually traffic flow though. Okay, right, so at this point, we suddenly realize we can accept discontinuities into the integral form of the conservation law. And the issue is that we've always been using the differential form of the conservation law. And in some ways, it's a bit more restrictive because of these things, these space derivatives, it doesn't actually allow you to easily deal with discontinuities. Another way of saying that is that the integral form of the conservation law is the more fundamental way of writing the system. The differential form is not. Right, so having said all of that, now let's revisit the problem that we dealt with down there. Let's revisit pileup. All right, so I'm revisiting pilot. I have a solution that I know was good up to t is epsilon over rho. That's what I had before. Now we want to go beyond. And how do we do that? Well, we avoid a multivalued non-unique solution. We don't want that at all. Instead, we're going to say that we have a discontinuous solution. So let's work out the details. So back to the pilot problem. For t equals epsilon over rho 0, a discontinuity forms. And now we're going to call it a shock. And if I think about the picture that I drew, I have rho is equal to 0. There was a step up to rho is rho naught at this original position. Well, I have to figure out what that was. So that's going to be x star. Okay, that's going to be x star at a particular moment here. We have rho minus, that's the value on the left, is equal to 0. We've got rho plus is rho naught, that's the value on the right. So that means that dx star by dt is equal to, using the previous results, I may as well put them over there. We've got dx star by dt, that was j plus minus j minus over rho plus minus rho minus. And when we wrote that, we've got that j. So replacing the j with the rho, that's rho plus times 1 minus rho plus, that's j plus. There's j minus. So we get that. And actually, the first term there and there, that's rho plus minus rho minus, which is that. So I get a cancellation, I get 1. That's minus rho plus squared plus rho minus squared, which I can factorize. I can cancel off a rho plus minus rho minus to get there. So for our particular model problem, which I may as well continue with over here, the actual shock speed is 1 minus rho minus minus rho plus. And for the values that I've got there, that's just 1 minus rho 0. Okay. All right, so what this tells us, right, is that the characteristic solution that we were dealing with to begin with, it's okay until things go vertical, right? When things go vertical, a discontinuity appears, and then we can use this theory that we have for discontinuous solutions, which tells us that we keep this discontinuity and it has that particular speed, right? So we've got this jump, this thing starts to move, and it doesn't matter where it goes, it's always going to have a value on the left which is 0 and a value on the right which is rho naught. Okay, right, so now let's just complete the analysis of the problem. Okay, so if I go back and I look at this, that was the solution, by the way, that we had for minus epsilon plus t and epsilon plus 1 minus 2 rho 0 t. That was that interval. And actually what you can see is that when t is equal to epsilon over rho, right, so that one approaches epsilon rho naught to the minus 1, If I do the same thing here, I find that this also approaches epsilon to the rho naught minus 1 minus 1. That's for t going to epsilon over rho 0. Right, so we had this ramp, right? The ramp was getting steeper and steeper and steeper, and the end points of the ramp, they come together. And they come together at that particular point. Right? That would tell us that we need to solve this subject to x star is equal to epsilon rho naught to the minus 1 minus 1. That's where the discontinuity first forms at that point in time. Okay, so the pile-up problem has the following solution. X star is equal to epsilon rho naught to the minus 1 minus 1. That's the initial position, plus the speed, 1 minus rho naught, times t minus epsilon over rho naught. Actually, there's some cancellations if you're willing to work at that a little bit, because that thing works out to be just 1 minus rho naught t. So there's the shock. So one last thing. Let's now revisit the characteristics diagram, given this information. And it's going to be beautiful. So, there's one part of the characteristics diagram that's the same as what we had before, which was that between minus epsilon and plus epsilon, we've got these characteristics. Remember, this one was going this way, this one's going that way, like this. These ones are coming this way, and these ones are coming up like that. And this remains true, provided we don't go too far. But at some point, what happens is that there's a point here that corresponds to this time and that position, where all of a sudden there's a disaster because all of these things start to cross. I guess I haven't drawn it very badly because they all cross at once, actually. Let's try again. So they all cross at once because the entire ramp becomes vertical at the same time. So there's something that looks like this. So that is the picture that we had from before, redrawn slightly, a little messily. Now, the issue was that we can't accept the multivalued solution that we get after that particular time. Instead, right, so this is t is equal to epsilon over rho naught, that point there, that's x is equal to epsilon rho naught to the minus 1 minus 1. Right, at that point, we get the development of a shock, and I can put its path on, which is this, right? It's some straight line that looks like that. So this is x star of t. Right, so what's happening is that there are all of these characteristics that all crossed at once there, and then I'm just going to remove them. I surgically snip them off. At this point, I can actually continue everything. Right? So these characteristics are still there. They're from a part of the solution that remains single valued. Boom, they just propagate in, hit the shock. These ones do the same. They hit the shock from that side. So the shock consumes the crossing characteristics. that makes everything fine, right? And we've got this discontinuity that removes any possibility of multivaluedness. Now removes the non-unique multivalued solutions. And we figured out what happens. Okay, so let's end this particular session.